Okay, even for the last one, forgot to record. So on this question, we're doing one of the questions on the final exam review worksheet, and it asks us it tells us the delta H of neutralization for adding a strong base and strong acid together, and asks us to figure out how much heat is produced. And so when it says the H of neutralization of adding a strong acid, strong base, it's basically telling us the H of this reaction right here. So now we know that delta H for that reaction right here is this. So we can use these two amounts to figure out how much H plus we have, how much OH minus we have. So it's just the limiting reactant kind of problem. Okay, so that's what I'm gonna do when the actual recording of the time starts. All right, YouTube. Okay, so 50 milliliters of my HCl, right? HCl. That would have been bad. Oh. Okay, HCl, and then 0.100 molar HCl. Oh, well, I'm gonna make these liters. I'm skipping steps. So this is 0.050 liters, and then for every 1 liter, I get 0.100 moles of HCl, right? That's just my molarity. And then I should technically be careful here. So for every 1 mole HCl, I get 1 mole of H plus. And then for every 1 mole of H plus, I get negative 57.3 kilojoules. That's going to be something. And then one more, do it same thing for our NaOH. So you get 0.035 liters NaOH. And then we get 1 liter, excuse me, for 0.13 moles. And then for every 1 mole of NaOH, I get 1 mole of OH minus. And then again, for every 1 mole of OH minus, I get negative 57.3 kilojoules. Okay. If anyone's calculated those numbers, that would be great. I'll do them as well. You wrote 0.01 instead of 0.01 moles. Oh, you're right. Good catch. 7.3. So I have for the top one, how many suffix do I want? Probably 3. So negative 0.287 kilojoules. And then for the next one, is it 3.5? I got negative 0.261 kilojoules. I remember from our limiting reactant problems, we picked the smallest one, so choose this one. Okay, hopefully that's answer. Let's see. Is that the right answer? Yes, good. So it's A. Let me show you. Bam, there it is. They put it in, we had it in kilojoules, they have it in joules, and then they have positive. So, because they are, heat released. They're saying heat release. So technically, this is being released. So I just flipped the sign, if that makes any sense at all. Why is it the 0.261 again? It's a smaller one. So we were doing, so this is kind of just us seeing how much heat this produces. Oh, you can't see that. So in both these cases, I'm just trying to see how much heat does this produce, this by itself, and that produce, right? So if I just had this in excess HCl, it would produce that much heat. If I just had that in excess NaOH, it would produce that much heat. So obviously, if I mix these two things together, this is the smallest one. Or is that what you're asking? So this is the smallest one, so I picked this one. And then they just converted it to joules. So they did 261 joules, which is A. No problem. Okay, let's see. Let me see if there's a wavelength. I wonder if there's a wavelength in here. I don't think there is. I don't remember seeing one. Okay. Now's your chance to, if anyone has any questions, ask now, because I'm about to find a wavelength problem. It's not 7.6. Here we go. Okay, because heat release, so wait, why do we flip the sign again? Oh yeah, because of the question says release, so you flip the sign. I just want to do more titration problems. We will get to titration, Junior, I promise. Okay. That's my one thing I'm absolutely doing. Okay, I'm gonna erase this. It's gone now. So let me remind you, for waves, we had well, our two main things. So we had C equals lambda nu, and then we had E equals H nu, where H is Planck's constant. And that's a number. Ooh, what is Planck's constant? It's like it's a constant. Where is it? Hello. Anyway, I'll come back to that. So this is frequency. This is also frequency. This is wavelength. And that's the speed of light. That's the speed of light. Right, because all this stuff we were doing EMS, and that's 3.00 times 10 to the 8th meters per second. It's kind of crowded. Three 0.00 times 10 to the 8th meters per second, speed of light, and that's the wavelength. this is energy per photon. Great. So let's see. Oh, there's H. Okay, Planck's constant is 6.63 times 10 to the negative 34. 6.63 times 10 to the negative 34 joule seconds. Joule seconds. Another thing that we could also use to find this for E is we could have said E equals and then solve for our frequency up there is equal to H C, yeah, C over lambda, right? That's the same thing because this is just our frequency. That's new. So the main wavelength kind of problem is just going to be like, especially since it's multiple choice, they're going to give you either the energy and ask for the wavelength. Maybe they'll give you the wavelength, ask for the frequency, you know, stuff like that. They'll give you one and ask for the other usually. So one simple one I saw, where to go? That's not it. Yeah, they gave you the wavelength. So they said the wavelength, here's our question. The wavelength is 705 nanometers. And they want to know what the energy is, energy of a photon. All right, not too bad. So we're just going to take this guy right here. So we'll say E equals my H, which is 6.63 times 10 to the negative 34 joule seconds. Oh, I need more space. Move it over. E 6.63 times 10 to the negative 34 joule seconds times my C, which is 3.00 times 10 to the negative, not negative, 8 meters per second. Okay. So I go plug in my lambda, and the main mistake people make here is that the C value and your lambda value have to agree in units. So here's in nanometers, but in my equation I put my speed of light in meters per second. So I need to put that in nanometers. I need to put this in meters. So I go to my conversion thing, and remember that a nanometer is times 10 to the negative 9 meters. So this is 705 times 10 to the negative 9 meters. Okay, so that's what I put here. And then I get E is number. Times 10 to the negative 9. 2.82 times 10 to the negative 19 joules per photon. Okay. That would be my number. All right, so that's how most of this is going to go. There's one, I guess we should, there's one, DeBroglie as well. I don't know how much you're going to need that. But DeBroglie is like with any, so my DeBroglie wavelength is my Planck's constant over the mass of the thing times its velocity. So this is DeBroglie. DeBroglie. Can't see that, but so this is like saying things that you think are moving straight. So things you think are just moving in a straight line can also technically have a wavelength. Okay. All right, who asked that? Evelyn? Did that help? Yes, awesome. Okay, and then, yes, rate law. So rate law. I think so determining the rate law, I'm guessing, is what you're concerned with. Ooh, excuse me. Erase this. I couldn't hear what you said about DeBroglie. Sorry. Oh no, it's fine. So DeBroglie is just like if something was moving straight. So if I think something is moving in a straight line and I have its velocity and I have its mass, I can assign it a wavelength technically, right? Well, not technically. It does have a wavelength. So straight line has a wavelength. Okay, so that's all I said. Nothing else really important. Ooh, almost hit end meeting. That would have been bad. Let's see. Let me go get a rate law thing. Add one over here. Like that. Here. Is there? Oh, there's one in his thing. Let's look at this. Okay. Yeah. I like this. So we'll do this for rate law. Number this. We'll just determine the rate law. I'm thinking that's what your question's about. Okay, I'm gonna write the table over here. So we got 1, 2, 3. Got our H mercury oxide. We got a HA. Got the rate or initial rate. Technically, I'm just gonna put rate because I'm lazy. We got 0.180, 0, 0.180. We got 0.0170, 0.0170, and then 0.0340. We got 450 times 10 to the negative 5, 9.00 times 10 to the negative 5. My 4s and 9s look the same. Okay. 1.80 times 10 to the negative 4. Okay, so we're doing number 1 for chapter 14 and on his little mercury related questions thing. So that's what I'm looking at. Stop that. So here it is. Here's the gist of it. So we're going to determine the rate law here. And so for doing that, remember what we want to do is pick two. We're basically going to compare two experiments. So these are my experiment numbers. Compare two experiments where the rate, where one of the reactants doesn't change and the other one does change. So for the first one, because we're trying to figure out this, we're trying to figure out when does rate equals K times HGO, mercury oxide, times my HA, right? And we need to figure out these exponents, right? Because I can't just look at the reaction in this case, unless I can't look at the reaction. So I pick, so I'm going to do, let's do 2 and 1, right? HG changes, but HA doesn't. So we'll do 2 and 1. So 2 over 1, do it lower. 2 over 1. So I have my HGO, and this is going to be my 0.360 over my 0.180. That's 2. hopefully. So check that, please. I think it is. Quick maths. Rate. We got what? We got 2 is 9.00 times 10 to the negative 5 over 4.50 times 10 to the negative 5. And this is also 2. Sure. Is that, hold on, 9. Pretty sure it's also 2. Yes, okay. 2, yes, okay. So 2 to the, we're doing HGO, so it's x, 2 to the x equals 2. So I need x is 1. Right. Okay. So this x right there is a 1. I'm going to put a 1 right here. All right, I'm going to do the same thing. Same thing for the HA. So I need, so in 1 and 3, HG stays the same, HA changes. So let's do that. So 1 to 3, don't want 3 over 1. Okay. So I have, so for my HA, I have 0.0340 over 0.0170. That's 2. Hopefully 2. And then my rate is going to be my 1.80 times 10 to the negative 4 over my 4.5 times 10 to the negative 5. Can't do that one in my head. Is 4. Okay, do the same thing now, except with the y now. So 2 to the y equals 4. So the y needs to be 2, right? 2 squared is 4. So y is 2. So there it is. There's our rate law. We have it. Questions about that? Okay, I'm not seeing any. There's who asked me that about that? Sierra? Is she even in here anymore? No. Oh, okay. Well, she'll get the recording. That's good. Anyway. Is everyone good on rates? Rate law, or at least doing this? Yes. Okay. Not sure. So let's do some titrations. How's that sound? A titration problem. How does everyone feel about that? It's one of those. It's one of those. The not multi-purpose, but multi-volume ones that I just found off the internet. So we can do all, well, not all situations, but most of them kind of, cover all bases of titrations. Where's my thingy? Here it is. Is that it? Yes. Yes. Do that. Do this. No, it's okay. Okay. You can't see it yet, I know. Here we go. Let's do some titration stuff. Here it is. Some weird numbers, but it's okay. Okay, so we got 35 milliliters of 0.040 molar HClO2, and then we got 0.097 molar lithium oxide hydroxide. And then we're gonna write those down, those concentrations down somewhere else, so I'll remember. You can tell I made this problem up because one of the numbers is not round. Or it has a weird decimal place. Okay, all right, here we go. Here we go. Titrations. Okay, the first one, the easy kind of layup one. So when I add 0 of this, 0. Ooh, I need a Ka. Oh no, I forgot the Ka. Rip. Hold on. Hold on. Hold on. So Ka equals 1.1 times 10 to the negative 2. Okay. Whatever, fix it. There we go. Now we have Ka. Now we can do it. Right, so this is our, so if I add 0 of this, it's just fine. Tell me the pH of that much HClO. So I do my acid thing. See, so we do our acid HClO2 plus my H2O goes in equilibrium with the so it's acid is going to donate its thing. So ClO2 minus plus H2O, not H2O, H2O plus. Right, do my ice table, ICE. Right, my 0.040 goes there. Here I get 0 and 0. Don't care about those two. Minus x plus x plus x. And I get 0.040 minus x, x, and x. Right. Now I just set this equal to my Ka. We solve that. isn't HClO2 a strong acid? No, I think it's HCl3, ClO3, and HCl4. Those are the stronger ones. I think. I'm pretty sure. Oh, okay. That's fine. No, I'm going to be nice, actually. Let's do that one. I'm going to be nice and get rid of that. I was thinking I was going to be mean, but anyway, we'll do this. Make this easier. Because I don't think he'll do that to you if he does ask you this. So he'll be 2.9 times 10 to the negative 8. So when it's not strong, you add it to H2O. So, okay. So if it was strong, if this was strong, if that was a strong acid, and I was just looking for the pH of that, I would just take this concentration as my H plus concentration. Because for strong acids, well, for most of them anyway, the concentration of the acid is going to be equal to the concentration of my H plus. Right. So this is, if it's strong, the acid concentration is the same as your H plus concentration. So just take the negative log of your, we would just take the negative log of that if it was strong. Yeah, okay. So I was thinking about making, so before this was like 1.1 times 10 to the negative 2, so we couldn't make our x a small assumption there. So I changed it so we could. Okay, so we do our 2.9 times 10 to the negative 8 is equal to x squared over 0.040 minus x. Right, we're going to assume x is small, get rid of this. Right, 10 to the negative 8, 10 to the negative 2, that's greater than 10 to the negative 4. So, or that's a farther distance than 10 to the 4. So I can make that. Then I solve for my x. Okay, here's the part where I mess up. Oh, calculator, don't round it so badly. I got 1.16 times 10 to the negative 9. Maybe I'll just keep going until someone tells me that's wrong. Okay, so that's, well, first I should check it as a check. So I need to make sure it's less than 5%. So 1.16 times 10 to the negative 9 over 0.040 times 100. Up, take the square root. There you go. See, told you I mess it up. Dang it. Always do it. I should have thought that number was kind of small. Thanks, Shania. There we go. Got excited. Times 100. We got, what did I get? Got 8.085. 0.085, definitely less than 5%. This is percent, less than 5%. So this guy's good. Rolling along. So now I do pH is the negative log of my 3.41 times 10 to the negative 5 pH negative 1. I got 4.7. 4.47. Yeah. Bam. Make sense, right? That was kind of chapter 16 stuff, but we should talk about it anyway. Yep, okay, good. All right, sanity check, that's acidic. We did it for an acid, so we're good. All right, nothing too bad there, I hope, except for me forgetting the square root things. All right, let's do, okay, let's do the next part. Okay, I think the next one's 10. So we do 10 milliliters of our lithium hydroxide. So let's see, let's do the, okay. So the first thing that's going to happen is this reaction. So the reaction between my H, the ClO plus lithium hydroxide goes to my lithium ClO plus H2O. Right. You could also write this like H. You could also write this without the lithium in it. So minus and minus. Either way, I'm going to do it this way. This way makes more sense. Right, because this lithium hydroxide is going to completely disassociate, and the only thing that's going to react with this acid is this hydroxide part. So either way, either with the lithiums there or without them, you get it's the same thing. Okay. So now we should calculate the moles of both of those. So the moles of this is what, 0.0, can you see that? 35? Right, liters times my 0.040. And so then this one is 0.010 times my 0.097. My zeros look weird. 0.0. So I got 0.0014 right there. And then we got 0.00097. And then 0 right there. Don't care about this. Don't care. Not gonna write anything. All right, here's our limiting reactant thing again. So this is the smallest one. So I'm going to subtract this from everything. 0.00097 minus 0.00097. And then on this side, because it's a product, I add the 0.00097. Okay. So I do my, so this is 0. So I do the subtraction addition, so that's 0. This is 0.00997. And what is this over here is this minus that. 0.00043, right? And these are all moles. Moles. I'll put moles just down here. Okay. Bam. So we have our acids. Oh, phone, please. Okay. We have our acid sitting right here. We have our buffer, or not buffer, I gave it away. We have our acid, we have its conjugate base. So we have a buffer going on right here. So we go look in our equation sheet, grab our Henderson-Hasselbalch, Hassel, whatever it is, pH equals pKa plus the log of the base, so A minus, over the acid. Right. Usually those are concentrations, but again, since we're going to divide them by the same volume, okay. How come we subtract the limiting reactant on this one, but we didn't have to do anything on the first example? Because this reaction didn't happen on the first one, right? I mean, it did, but here we subtracted 0 essentially, right? Because there was none of this in there. It had 0 milliliters. See that, right? Because in the first one, yeah. So if it is adding an acid, we do, but not a base. So if it is, I'm confused what you're asking me. Because in the first example, I had 0 milliliters of this. So this reaction doesn't happen. So basically I get 0 there, right? And then I would subtract 0 here and add 0 there. So I would just be left with what I started with. And I just need to find the pH of this. Yeah, yeah. So the first one, basically you could ignore this line because I wasn't adding it. It's just asking what's the pH of this concentration. But now since we're adding this, we're adding some of this into it. We have this a reaction going on first, and then we find the pH. Okay. So we got our pKa, right? So this is the negative log of the Ka, so 2.9 times 10 to the negative 8, plus the log of, we're using moles here because we're using moles here since what was I going to say? The moles of the, oh, fine. Okay. The moles of the, since we're going to divide by the same liters, I can cancel, like a liters cancels out. 0.00097 over my 0.00043. And so I get my pH is equal to calculator, here it is. Let's see, 2.9 times 10, 8. Okay, so what did I got 7.89. My pH. It's weird, but okay. All right. Questions on that? So we don't need an ice table here because it's a buffer. And well, the ice table is kind of like embedded in this equation. So if it was just that, so either if it's only this acid or it's only that base, then you have to do an ice table. But in our case, we have both of them, so we can use our buffer equation. Great, no problem. So yeah, you have both of them, use a buffer. If you have one or the other, then use an ice table. Any other questions? We'll get some water. Awesome. I'm not seeing any, so we'll move on to the next part. So erase my stuff I have here. Oh, if you have KB, how you get KA. So it's actually the next part. So if I have so up here I have KA, hopefully that's what you see, it's KA. So if I need KB, which is I do in the next part, so this is a good thing to do right now. I take, it's KW over KA, right? It's KB. And then KW would be given to you. So that's 1.0 times 10 to the negative 14th over the 2.9 times 10 to the negative 8. So KB, in this case, oh, if you have same thing. Oh, sorry. So if instead you were doing this and you had like a base right there and you had KB, you just do this, but do KA equals KW over KB. Sorry, I misunderstood your question, but do that. You'll have this. That'll be given. So you have both of those. So calculate Ka and then put that in here. Yeah, this equation doesn't change if you have acid or base, like as your starting thing. It's general for all things. So you always need Ka, and it's always the base part over the acid part. So do this to get your Ka, and then you plug it in to get pKa. No problem. Okay. Okay, so almost, I'm going to calculate KB since I started to already. What, I get 3.45 times 10 to the negative 7. Okay. All right, so we're gonna need that for the next part. So I'm gonna solve this, don't need it. Hopefully this is helpful. Make this. Okay, change this to I think 14.43, right? That disgusting number. All because I made this up and wasn't smart with my numbers. Okay. Okay. Right, I'm just adjusting, do the same, doing the exact same methodology. Oh, that's gonna change. Right, but that guy doesn't change. So I got 14, 0.01443 times that. I'm hoping if I did this right, get 0.0443 times 0.097. Got, yeah, 0.0014 from rounding. That's zero still. So subtract both. Subtract both. It's zero there, and plus 0.0014 moles. Right, okay. So here's the, please, okay. Here's the other case. Right now I just have my base part sitting in there. So that's why I need a KB, because we use that to solve the ice table for this. But again, that's moles. For our ice table, you need molarities. Right, so we need to divide this by our volume, which is our 35 plus that 14.433, 14.43. Okay, so 0.0014 over my 14.43 plus 35, and I get, so, oh geez, I didn't do it right. 14.43 plus 35, almost messed up again. Fixing it now. So 0.0014 by this is, so divided by 0.04943, and I got 0.0283. Ooh, okay. All right. Okay, so now we just find the pH of this much of that. So gonna add it to water down here. CuO minus, gonna get kind of cramped, that's okay. Plus H2O goes to my HClO plus my OH minus. Do my ICE. Right, correct. So this is where my 0.0283 goes. Don't care. 0, plus x, yada yada. Did it earlier, same thing. 0.0283 minus x, and x. Go over here. So now I do my 3.45 times 10 to the negative 7 equals 0.0283 minus x over x squared. Oof. We're rolling. Okay. X is small, 10 to the negative 2, 10 to the negative 7. That's greater than 4. Get rid of this guy right there. Okay. Now we solve for x. Hopefully not mess it up this time. Where'd it go? There it is. taking the square root this time. Oh, hold on. Oh, moment of truth. 9.89 times 10 to the negative fifth. Maybe. Awesome. Good. Okay, gotta check it again. Or check it. Check it right now. So we do our 9.89 times 10 to the negative fifth over the original. So my 0.0283 times 100. Oops. Calculated them like that. The answer over 0.0283, yada yada, times 100. Get out of scientific notation mode. Sorry, I'm talking myself. Oh, not that one times 100. Whoops. This. Okay, I got 0.349. So this is good. Final leg. Oh, well, kind of final leg. All right. So it's OH, right? We're dealing with bases this time. So OH here. So I'm going to calculate POH is my negative log of the 9.89 times 10 to the negative fifth. And so my POH is negative log of 9.89 times 10 to the negative fifth. So 4.00. So I mean the pH, just 14 minus that, so it's 10. Bam. Bam, we just found the pH at the equivalence point, right? Equivalence point because those two have the same amount of moles. Questions on that? No. Okay. How did you know to use KB instead? Because this, so yeah, so since this is an acid, I know that's an acid, so this is its conjugate base, right? So when this is a base, so I need a KB. So anytime, phone please, okay. Anytime you have, yeah, okay. Anything else? The last one shouldn't take, this isn't gonna take as much math. Not seeing anything. So I'm gonna assume we're all good. Cool. All right. Last part of this titration problem. I'll leave that just in case I need it. I don't think I do. Pretty sure I don't. Confident I don't. Okay. So this changed to 20, I think. 20.00 milliliters. Ooh, excuse me. So I get right here, same thing, 0.020. The 0.020, and then multiply that by that. Numbers, please. is 0.0094, 194. Okay, it's still 0 right there. Now this is the smallest one, so we subtract 0.0014 plus 0.0014. Minus 0.0014. We got 0.00054 and then what, 0.0014. So this is literally pure OH minus, right? Either pure OH minus or the strong acid part, depending on how you wrote it. So this is going to drive the pH here, and we're just going to ignore this part. This part we can ignore and just focus on what this is going to do to the pH. So let's look at this. So I just need to find the pH of this, right? So I can get POH immediately because that's the OH concentration. So POH equals negative log of 0.00054. So my POH is 3.277, and so my pH 14 minus this, so 10.73. Bam, there it is. Easy. Shouldn't you calculate M? Yes, you're right. I got excited again. Oh, good call. Actually, I was testing you. You passed. I wasn't. I messed it up. I got excited. Okay, let's divide it by let's divide this is moles. I forgot. That's divided by, hear that? Exciting. This is final exam extravaganza. What's that, 55? Liters. So what's that? That is what? Was that 9.82 times 10 to the negative 3? Hopefully. Then now I can finally do my POH, right? Negative log 9.82 times 10 to the negative 3. The POH. Negative log this, oops. 2.01 pH is what? 14 minus that, so like 12-ish. 11.99. Bam, better. Better is because it's right? Got a little excited. Okay, so when you are past the equivalence point and have only base and conjugate base left, you use this. Yeah. Same thing if it was like you have a strong base and a conjugate, a weak base. So you only look at the strong base. And same thing if it was flipped for the acids, except you would just calculate pH because you just have a strong acid right there. So yes, this is what we're basically just ignoring this weak base because it's not going to contribute that much. Questions, titrations, or anything? Okay. Not seeing anything. Let me go look at my questions and see what other things. Here it is. Let's see what else. Very important. Can we do a precipitation problem? Yeah. So maybe something like, so would like precipitation, complete precipitation be okay? So like if I ask you if a precipitation of something is complete, here, I'll show you so you know what I'm talking about. Hold on. Let's, yeah, something I want to change when I type it. Let me share it with you. Here we go. Share, please. Share. There we go. Is this one? Okay. Let's erase this. I need it. Okay, so what we got? We got 500.0 milliliters of 0.0080 molar NaCl, and then 300.0 milliliters of 0. Don't make the of 0.040 molar AgNO3. Right, and I'm asking you if the precipitation of Cl minus will be complete, and basically what that means is after, like when we do our KSP thing, and at equilibrium is the concentration of Cl minus 0. So that's the question. Okay. Then I give you the KSP of AgCl. All right. So, okay. Hopefully you got that. So I'm asking for a completeness in the precipitation, right? I told you that the KSP, I just should have wrote it down. KSP of AgCl is my 1.6 times 10 to the negative 10, right? So since I told you that, I was, so what you might do is not tell you this in the question, but give you a table. I don't know how to do it. I might just give it to you. But if anything, if he doesn't tell you the KSP in the question, you have to figure out what KSP you need. You could always just do, so AgNO3, so that's aqueous, plus NaCl, it's aqueous, and then you would do your switcheroonie. So, oh, not plus, goes to AgCl plus NaNO3, right? You would see this was aqueous from your solubility rules, and this one was solid. Right? You do your net ionic equation thing, right? Break that up, break those up. This stays, that stays. Get rid of your spectators, and you would get Ag plus Cl minus goes to AgCl solid. Right? And that'll tell you to go grab the KSP for this guy. Or you could tell it from up here. Grab the KSP of that. Just the only thing to be careful of here is that the KSP is for the flip of this reaction. So so I don't mess that up. So KSP is for this one right here. Cl solid goes to Ag plus Cl minus. Okay. All right. So we're doing our ice table right here. That's a solid, don't care. But we do have some initial amounts up here, right? These things are soluble, so they're going to completely break up. So I can calculate my Cl minus concentration from that. So I do my 0.500 liters times my 0.008 molarity, and that, okay, figures I'm doing. That gives me what? 0.5, I guess 0.004, right? Yep. This is moles Cl minus. Here, do it again for Ag. So in here, right, 1-to-1 for both of those conveniently. So 0.300 liters times my 0.04 molar, and I get the 0.3 times 0.04, 0.012 moles of Ag plus. And then, okay, so again, for our ice table, we need molarities, right? That's mostly for me. So we need to divide by our total volume, right? So I did 500 milliliters plus 300 milliliters. So that's 800 milliliters, so 0.8 liters. Divide both of these by 0.8 liters. So I get 0.005 molarity, 0.00, no, I didn't even do that yet. I was writing it. Also, I don't know if I said this, but feel free to stop me. I think you already did. You already did that last time when I messed up. Never mind. Okay, so this is the molarity of Ag plus, and this is the molarity of Cl minus. I don't know if you guys can hear them. I can hear like my roommates in the living room. It's crazy. Okay, anyway, so now we could use our ice table. We'll throw it up here in our ice table. So 0.005, 0.0015. Oh, no, 0.15. 0.015. Why can't we use the 0.008 and then 0.004? Because you're diluting them, right? You're mixing them together. Like you're taking that much of this and that much of that and mixing them, so you're diluting the concentration. So if I had not mentioned that I was mixing, like if these solutions are already just sitting in there and these are the concentrations of the final solution, then you could just use those. But since I'm taking two separate solutions and mixing them together, I'm diluting them. So I have to do this. Okay, so here, we have to make sure that this thing is going to shift that way, right? Because the only way that this drops to zeros if the reaction shifts this way, right? And there's no way to tell because you have whole numbers on both of these sides. So it could shift that way. It could even shift this way for some reason. So we got to do our KQ comparison. So I'm going to calculate Q down here. So Q equals my 0.005 times my 0.015. So Q is what? Was it 7.5 times 10 to the negative fifth? Oop. Okay, so we do our K versus Q versus Q, 7.5 times 10 to the negative fifth, 1.6 times 10 to the negative 10. Right, Q is greater than K. You can kind of see that Q is greater than K, so you are in fact going to the left. So that's good. So we put minus S, minus S. Okay. Okay, so 0.015 minus S, 0.005 minus S. Okay, gonna set that equal to K, set this equal to my K. So my, 1.6 times 10 to the negative 10 equals 0.015 minus S, 0.005 minus S. All right, got to be careful here. Your first instinct may be to jump to assume S is small, but if you do that, you get rid of both of those. Right, both of those disappear, and you can't solve for S anymore because S is gone. So we can't do that. So another thing would just solve that quadratic, right? Multiply it out. Solve the quadratic. Okay. So what is the quadratic? It's going to be S squared. So minus whatever 0.015 plus 0.005 is. So 0.02 S. Right, I'm doing my FOIL, so this times that plus this times that, and then plus it's 0.00075, that's the 0.015 times that, and then minus this guy. And so plus the 7.5 times 10 to the negative 5, 5 equals my 1.6 times 10 to the negative 10. Sorry, you can't see that. It's just that. This is the same thing. And then I subtract this guy over, so S squared minus 0.02 S plus 7.5 times 10 to the negative, that minus 1.6 times 10 to the negative 10, not 5. You get basically the same thing. 7.5 times 10 to the negative 5 equals 0. So S is going to be 0.005 and then 0.015. Right, those are the two answers I would get. So right, it can't be that one. If it was that one, you would get a negative equilibrium. So it has to be this guy. So ignore that. It has to be this one. Okay, all that work got S, not done yet. We have to check to make sure that my Cl minus concentration is going to be 0. So again, for my Cl minus is going to be 0.005 minus 0.005. So Cl minus 0 at equilibrium. So the precipitation of Cl minus is complete. Okay, there's my answer. Questions, comments, concerns? 9:30, not bad. Not seeing any. Let me go look and see other problems we can do. See what we got. Ooh. Should we talk about reaction mechanisms? Do you remember that? No. Okay, so we'll look at this one. This was the issue problem, or the harder ones. Gonna get your blood pumping. Okay, so this is rate law stuff. In chapter 14, or kind of the end of chapter 14, we're talking about reaction mechanisms for, stuff, how related to our rate law. So here's one of the types of problems you could have been asked: is prove that this proposed mechanism is in fact is a possible mechanism for the reaction at the top. So let me, gotta stretch out my back. All right, stuff. Trucking along. Oh, my toes. Okay. I should write this. Okay. So 2H2 plus 2NO2. Oh, not NO2. NO goes to 2H2O plus N2. Also, can you tell I just copied pasted exactly from this PowerPoint? Rate equals KH2 NO squared. Oh no, I'll need way up there. Okay. Great equals KH2 NO squared. I need my mechanism, so 1 is NO, 2 of them. Gas goes to N2O2, 2 H2 plus N2O2 goes to H2O, and then plus N2O, and then 3 is that H2 plus N2O goes to H2O plus N2. And then someone just drawn here. What we got? This one's fast. This one's slow. This one's fast. Okay. All right, over here. That's the gist. We want to prove that this mechanism is viable. All right, here we go. Here it is, wrote it out. Again, excuse me. What was I saying? So here are all the steps. So first thing we have to do to make sure this is viable is make sure that these 3 reactions add up to that top one. So if I add them real quick, I see, okay, I get 2 NO2, or 2 NO, right? That doesn't cancel anywhere. Nope. Plus 2 H2, those don't cancel. Those go away. These go away. And I get goes to 2H2O plus N2. All right, so that's the first thing I have to check. That passes that step. So we're good on that part. All right, so that one's check. Next thing we have to do is see if the rate law of this mechanism agrees with this rate law up there. Okay. If it would only cancel if a product is a reactant in the next step rate. So yeah, if they're on opposite sides. So you could have a mechanism. So I could have something like plus A and then plus A, right? That would still cancel because it's on opposite sides. So it doesn't have to be on the product side in one step and then the reactant in the next step. They just have to be on opposite sides. So if you see it on both sides, you cancel it. Good question. Okay. No problem. Okay, so now I need to make sure my rate laws match. So to get my rate law of this mechanism, I look at the slow step is my rate determining step. So it's going to be the rate law of this guy. And since these are in a mechanism, I can just use my coefficients as my exponents, right? The one rule breaking thing. So right now for my rate law, I have that the rate equals K, we'll call it K2 because it's the K of the second one, times H2 times N2O2, and that's it. Camera, please. Okay. Right. Anyway, so this is a problem, right? This is an intermediate. Right, because it was produced in one step. Oh wait, where did you get that? So this is just the rate law of this. I just looked at my, yeah, from the slow step, exactly. So just pull your reactants and just look at their coefficients. Yeah, this came from here. And so again, this is a problem because you can't have, this is an intermediate produced in one step, used up in the next. So we gotta move this guy essentially. So I look at my intermediates and I see, okay, I see that the intermediate was involved in this equilibrium, so that's good, because that in equilibrium, the rate of my forward reaction is equal to the rate of my reverse reaction, right? Maybe I should change colors. And then so for this, the rate of the forward, so going this way, is K1, I'll call it, times NO squared, right? Just reading off the exponents of the coefficients, and then I just do it for all the reactants. And the reverse reaction, so going this way on this first one, I'll call it K minus 1 times my N2O2, right? And this guy is not an intermediate, so this it'd be better to replace that with this. So that's what I'm gonna do. So I know that concentration of N2O2 is equal to K1 over K minus 1 times the concentration of NO squared. All right, so I come down here, take this guy, toss him straight into that. And so I get, let's do it this. I get that my rate equals K2 times H2 times my K1, K minus 1 times NO squared. Say that's the same as K2, K1 over K minus 1 times H2 times NO squared. This is all, I'm just going to lump that, smash that all together. So we'll call this K of our mechanism. So K mech, or K, just call it regular K, is H2 NO squared, right? Lo and behold, this is the rate. Lo and behold, that guy is the same as this one. So this is a good mechanism. Good or possible. Mechanism. Right, this is one of the harder ones. Questions on this? Questions or comments? Nope. Awesome. Okay, let me see. Anything else I can do quickly I want to talk about? I feel like CuCl2 D is not an issue. Well, we can do some colligative. Let's do colligative properties a little. Yeah, let's do colligative. We'll finish up with colligative properties. Or at least that'll be the last thing I talk about. Probably, most likely. Okay, no questions. I'm gonna erase this. So that's this one I want to look at. Finish up maybe. Here we go. Get ready, please. No, I'm talking. Okay. Okay, so here we got some solutions going on. So what's these little m's? I want these to be little m's. Boop. Okay, that's better. Right. Alrighty, so we have all these solutions mixed with water and we're looking for the highest boiling point. We're looking for the highest boiling point. Okay, my roommate walking around out there. Yeah, highest boiling point. Maybe write this down. Quick refresher if you need it. So we had colligative properties. So one of them was boiling point elevation. So to figure that out, we had the change in temperature is equal to, or the change in the boiling point, I should say, is equal to I, which is our Van 't Hoff factor. We'll talk about that in a little. I times my molality times my K of B, which is like a constant for your boiling point elevation. And this Van 't Hoff factor, this is the Van 't Hoff factor, maybe I Hoff factor. Essentially what it has to deal with is how many different ions does your thing break up into. So for non-electrolytes, I is 1. And for something like, try not to give away answers, LiOH, right? This thing breaks up into Li plus and OH minus. So my Van 't Hoff factor here is 2, right? So basically you're just counting the things to break off into. If I did MgCl2, it breaks up into 1 Mg plus and then 2 Cl minuses. So I get I is 3. Here, don't be tricked. The polyatomics stay together. Or assume constant. All right. So now we want to see which one of these is going to have the highest boiling point. So since they're all in water, this is going to be the same for all of them. So I'm just concerned with this I times their molality factor. Okay, we can already rule out pure water because that's going to be the lowest one, because all the rest of them are just going to be increased. Okay. The rest of these are just going to be increased, higher boiling points. So the boiling point of pure water is just going to be the lowest one. Okay, and then let's see. Okay, so now I should find this I times my molality factor for everyone. So let's do that for each one of these guys. So this one I is 2. So IM equals 2 times 1. That's 2. IM is 2 times 0.75 equals 1.5, right? IM equals 3, right? 1 copper, 2 chlorines times 0.75. That's too hard for me to do in my head. Is it 2.25? Yeah, 2. Oh no, camera, please. Jeez, someone's calling me. Okay, it's back. Okay, and then generally things that are a bunch of coppers, hydrogens, and oxygens are just non-electrolytes. So for this IM is going to be 1 times 2. And so that's just going to be 2. So here we got, this one's the highest one. So this copper right here, this guy is going to have my highest boiling point. So does pure water have the highest freezing point? Yes, exactly. Because freezing point is depression. So if I did freezing point, my formula for freezing point is delta T of the freezing point equals negative I M K F. And so all the rest of these would be decreased and pure water would have the highest one. So yes, you're right. Good job, Eugene. Why don't you take into consideration intermolecular forces, right? You mean inter, not intra. Intra would be the bonds. Inter. So why don't I take it into account? So it's because I'm not worried about the boil. If I would, oh, okay, yeah. So if I think what you're thinking is if I was just worried about the boiling points of each of these things individually, right, then I would just look at their intermolecular forces. But if I'm looking at them in a solution of water and I want to know the boiling point of that solution, I have to do it this way. Right, intermolecular forces tells me the boiling points of each of these things individually, how they kind of relate. But this is how I relate the solutions of them mixed together. Right. And we'll do. Don't forget the other two. There are 2 other. So there's vapor pressure. So P vape, do I remember, is the mole fraction of the solvent times the original vapor pressure of whatever the solvent is. There's no Van 't Hoff factor involved in this. I probably should double check that. I'm not exactly sure, but and then there's the other one that was osmotic pressure. So pi is the symbol we used for it, and it was I times M molarity RT. Molarity times the gas constant, universal gas constant, times RT in kelvins. All the kelvins. Let me make sure I'm not lying to you with this formula. That's the thing I tend to do. Yep, okay. Solvent, mole fraction, solvent, P vape. What else? Is there anything else I want to say? I've got nothing. You guys got any questions? Guys, girls? I hope I don't offend anybody with that. I hope I didn't overwhelm you with me just talking for 2 hours, almost. Or basically, I'm not overwhelmed. That's not the word. I hope I didn't waste your time. But oh, I should. So well, oh, no problem, Jania. Here's the link again. If you need it, I'll also look on the back of the chat. Would it be helpful? Would it be helpful for you if I sent all the Jeopardy games back out as on the same thing? Oh yeah, yes, okay. So I'll do that. I might just send it to everyone. I'll just send it to everyone. It'll be nice. So I'll send everyone all the Jeopardy games on the same thing, so you have it in one place. I don't know. There's nothing really. All the stuff I pulled are from Dr. Keene's stuff. So you can go back and look at the worksheets. No problem. You can go back and look at the worksheets and all the PowerPoints. The interactive videos, they might be helpful as well on his homepage, Canvas. So yeah, you feel free to message me on if you have questions while you're studying. Something comes up, can't promise how quickly I'll respond, but I'll try to respond as soon as possible. Yeah, thanks for everything. I hope this online stuff hasn't been too bad. You know, it's crazy for all of us. I usually like to do the surveys. I like to see what you guys think, what your comments are. And I also like to see because at the bottom of the survey, you get to see who wants also to become an SI next year. So I also like to see that. But yeah, I've heard nothing from it. But what else am I going to ramble about? Yeah, message me. If you ask me a lot, I might do a Zoom meeting. I probably will, honestly. If you just ask, you should do OChem next semester. Well, issue with that, I'm graduating, not going to be here. I'll be in North Carolina actually doing graduate school. So OChem, thank you. Also, I am terrible at OChem. Like this is the only thing I know from OChem. That right there is a benzene ring. What it does, I have no idea, but it is a benzene ring. The formula for it is C6H6. What do I use it for? No idea. I just know that that's what it looks like. But yeah, feel free to ask me stuff. I guess if you probably can ask me and we'll meet on Zoom if you needed to, if it's like super desperate, but I'm pretty sure all of you are fine. I'll post this as soon as I can so you can rewatch it, maybe hear some of the dumb things I say. It's been fun. Thank you for being nice. Thanks for the help. Be safe. Good luck in grad school. Thank you. I appreciate it, everyone. So yeah, no problem, everybody. Thanks for your reviews as well. No problem. Glad I could help. I'll see you guys. I'll see you around. Bye. I have to find the meme for the final. Still looking. you. Thank you, Jen. Good luck with all your studies as well.